Hello, welcome back to Short Lectures in Physics. And the topic for discussion today is reflection of light, the branch of science that deals with the studies of light rays striking a surface at various angles is known as ray optics or geometrical optics. In general, the light is supposed to travel in straight line paths, and those paths are called as light rays. Hence, the study of light rays striking a surface at various angles is known as ray optics. This explains phenomena of light such as reflection, refraction, formation of images in mirrors and lenses, etc. When a light ray strikes a surface, part of it gets returns back into the medium from where it has started, and part of it gets absorbed and part of it gets transmitted if it is a totally or partially transparent material. The phenomena of the light rays returning back in the same medium after striking the surface is known as reflection of light, and the surface is known as reflecting surface. So this is reflection of light. In this figure you can see xy is the a polished smooth surface, and a light ray is falling on it along PO direction. It is striking the light ray starting from P, striking the surface at point O. That is called incident light ray. If we draw a normal to the surface of the polished surface like ON, then the angle made by the incident ray with the normal is called angle of incidence and indicated by I. The light ray, after striking the surface, returns back into the medium that is known as reflected ray, and this returns along the path OQ, that is reflected ray direction. The angle between the reflected ray and the normal ON is called angle of reflection R. In reflection, the angle of incidence is equal to the angle of reflection. This is what explained in this slide. A ray striking from point P the surface at meeting the surface at point O, making an angle I, that is called angle of incidence, reflecting back along the OQ, that is reflected ray, making an angle of reflection R. The angle of incidence is equal to the angle of reflection. And also one more important thing you can notice, the incident ray, the reflected ray, and the normal all will be in the same plane. In regular reflection, means normal cases, the reflected beam always returns back in a particular direction, not in all directions. It will be reflected in a particular direction. Of course, this depends on the property of the reflecting surface or the condition of the reflecting surface. Suppose a ray is striking the reflecting surface at 0 degrees angle of incidence, that is normal along the line ON. Then the reflected beam will also return back along the same direction since R is also 0. So the once normally incident ray will reflect back along the same direction through reflection. The reflection, whatever we have discussed, the properties remain same whether the surface, reflecting surface is flat or curved. Let us see some more facts or properties of reflection about the images formed due to reflection. So the mirrors form a virtual image and it is always vertical. So whatever way the body stands in front of a mirror, the same way the image also. If it is vertical, if it is that is image also vertical. And the image forms behind the mirror. The distance between the object and the mirror is equal to the distance between the image and the mirror. So image formed in the mirror is laterally inverted. That means though it is standing vertical, but left and right directions are interchanged. The left side of the object appears as right side in the image, and right side of the object appears left side in the image. That is called lateral inversion of the image formed in mirrors. Now we will see some more points about the, the characteristics. So far we have seen the reflecting surface is horizontal and the light rays are falling on that at a particular point and then reflecting back along the reflected direction. Suppose we turn the mirror through an angle theta. That means the angle, incident ray position is not changed, only the mirror position is turned through angle theta. Then the reflected ray changes through an angle 2 theta. This simple geometrically we can do that. So if the mirror is rotated by an angle theta, then the angle of reflection changes by 2 theta. Suppose the object is coming closer or going away from the mirror with a certain velocity, then the image also comes towards the mirror or away from the mirror, moves away from the mirror with double the velocity 2u. So this is another property. Though the image formed in a mirror is virtual, you said it's not real, but you can cast it in a camera because whatever we see in the mirror, the image, acts as a object for the camera to take the photograph. And if you see an image photograph and a real photograph, it's very difficult for the person to identify which is real, which is the image, and which is the object. And one more important thing is, as we know, the light has got certain frequency and wavelength, and it travels with certain speed. In reflection, the frequency, wavelength, speed of light do not change; they remain same. Only thing is, the intensity of reflected beam decreases because of the partial absorption of the light energy in the medium. So once we understand about some facts about the reflection, let us see how images are formed in mirror. In this slide, you can see an object is placed candle before a mirror, and image is forming behind the mirror. Object distance, image distances are shown. Then the image formation is shown geometrically to an observer at a certain height above the object. The light rays from bottom part and top part of the object travels into two directions. Let's say consider two directions. It can be multiple as well. For simplicity, we have shown two directions. So from the bottom of the object, light rays are traveling, and they are reflecting back to the observer, observing the image. Similarly, from the top portion of the object also, two light rays are traveling, and then they are also reflecting back as part of following the rules of reflection, laws of reflection, to the observer eye. So if we extend the reflected light rays back behind the mirror vertically, as shown by the dotted lines, then the lines joining at the bottom will be the bottom part of the object seen in the image. Similarly, the lines extended from the reflected light of top portion of the object, they will merge at one point. That gives the top part of the object in the image. So you can see the image bottom part and top part clearly. Similarly, for intermediate points also, all angle of reflections we consider, they follow the same principle, and the image forms in the vertical but virtual and laterally inverted image. If it is a round shape object, then lateral inversion is difficult to identify. Now, it is possible to see multiple images of an object if you place two plane mirrors parallel and facing each other, and the object is placed in between them. Now we have seen only image formation in one image, one mirror. Now if we keep one more mirror on the other side of the candle facing the first mirror, then you can see multiple images. Any number of images can be seen. The image formed in the first mirror will act as an object for the second mirror. Similarly, the image formed by the second mirror will act as an object for the first mirror again. Like this, multiple images act as multiple objects for both the mirrors, and as a result, you can see multiple infinite number of images. Infinite number you can see when the plane mirrors are arranged parallel to each other and the object is placed in between them. So the distant images, as you see, go further, then the distant images looks fainter because part of the light energy is lost in reflection due to its absorption. So if the reflecting surface is perfectly smooth, then the image appears clear, otherwise faint. Generally also, the reflecting surface is smooth, very smooth, then the image appears very bright. If the surface is rough, that means even on microscopic scale, rough means not we can feel with the hand, but even on microscopic scale, if the surface is not smooth enough, then the reflection takes place in multiple directions known as diffuse reflection. That means reflection of light from an incident ray in multiple directions due to the unevenness or roughness of the reflecting surface. As a result, no image can be seen from the reflection process. Like a paper, if you see paper or some surfaces, you cannot see, images are not formed because the direction of reflection is in multiple directions, hence no image is formed. In this slide you can see the multiple reflections. As I said, the first object placed between the two mirrors acts as an object for the first mirror, then the image formed will act as an object for the second mirror. Like that, multiple reflections you can see whatever I explained in this slide clearly. Then, now we talked about the plane mirrors placed parallel to each other, and that is 0 degrees angle between them. Then infinite number of images are seen. Suppose the two mirrors are arranged at an angle theta, in angle of inclination is theta, and the object is placed in between them. Here also multiple reflections are possible, but they are not of infinite number. The number is decided by the angle of inclination of the mirrors. So if the angle of inclination is theta, due to multiple reflections from both mirrors, the number of images formed is given by n is equal to, total is 360 degrees in a circle, 360 degrees by theta, that is fraction of the angle of inclination minus 1. That is, number of images formed is given by n is equal to 360 degrees by theta degrees, whatever number comes, minus 1, and this is for even value of 360 degrees by theta value. Now let us see some numericals to understand the applications and behavior of the properties of reflection, whatever we discussed so far. Consider a light ray from an object O striking a mirror at a point P of mirror 1 ml and reflects along PQ and falls on mirror 2 Ln at point Q. So from point O, light is falling at mirror 1 at point P and getting reflected back to mirror 2. From mirror 2 at point 2 it is incidenting, and from there it is reflecting back along the QR. So the angle of incidence reflection for the first mirror with reference to the normal drawn at point P is I and R. Similarly, for the mirror 2, the angle of incidence is alpha and angle of incidence is V. But anyway, I is equal to R and alpha is equal to beta. Angle of incidence is equal to angle of reflection. Now, with reference to various angles indicated in the figure, means angle of inclination is theta. The other angles of triangle LPQ are theta, x and y. Angle of incidence for the and angle of reflection for the mirror 1 are I and R, and angle of reflection and angle of incidence for the mirror 2 are beta and alpha. All these angles you consider. Then we try to get the relation between angle of incidences for the reflection obtained from mirror 2 and with the angle of incidence at mirror 1 I. That is relation between alpha and I. We want to deduce an equation for that. So if you see the mirror 2 at point Q, angle Y is given by 90 minus alpha. Alpha is equal to 90 minus Y otherwise. But for obtaining Y, consider the triangle LPQ so that Y is equal to 180 degrees minus x plus 3. Because theta plus x plus y is 180 degrees, y is equal to 180 minus x plus theta, and x is equal to again 90 minus r, that is 90 minus I. So you will get 90 minus theta plus I as the value for y, because I is equal to r. So why should that in the alpha is equal to 90 minus y to get y alpha is equal to theta minus I. The angle of incidence at the mirror 2 alpha is equal to the difference between the angle of inclination between the two mirrors theta and the angle of incidence at the mirror 1. All other angles are not important. Another example from the same uh, condition of reflection between two mirrors is shown here. Here we said I1 is the angle of incidence and angle of reflection from the mirror 1, and I2 the angle of incidence and angle of reflection from the mirror 2. Again theta, x, y angles are from the triangle LPQ. Here we want to find out how much the total deviation between the incident and the finally reflected rays. That means if we extend the incident ray at the mirror 1, then the deflection of that ray from its original path to reflected path is given by d1. Similarly, from the mirror to the incident ray is along PQ and the reflected ray is along QR. So if we extend the PQ line further, then the angle of deviation for the ray falling on the mirror 2 is D2. That is the angle between the extended PQ line and the QR line. Similarly, D1 is the angle of deviation for the first ray falling on the mirror 1 from OP, angle between the extended line OP and the reflected line PQ. So D1 and D2 are the deviations produced due to reflections at mirror 1 and mirror 2. So D1 is given by, that is the deviation due to reflection at mirror 1 is given by D1 is equal to 180 degrees, total is 180 degrees minus 2I1, because I1 plus I1 angle of reflection plus angle of reflection. Similarly, the deviation D2 from the mirror 2 is given by D2 is equal to 180 degrees minus 282. So total deviation is equal to D is equal to D1 plus D2, that is 360 degrees minus twice of I1 plus I2. From triangle LPQ, theta plus x plus y is equal to 180 degrees. That is theta plus x is equal to 90 minus I1, y is equal to 90 minus I2. So theta plus 90 minus I1 plus 90 minus I2 is equal to 180 degrees. If we simplify that, I1 plus I2 is equal to theta, that is angle of inclination. Thus total deviation D is equal to 360 degrees minus twice of I1 plus I2 becomes 360 degrees minus 2 theta. That means whatever may be the angle of incidence, the total deviation produced for the incident beam through reflection from two plane mirrors placed at an inclination theta depends only on the angle of inclination theta, that is 360 degrees minus 2 theta. So I values are not, I1, I2 values do not come into the picture. So this is another interesting numerical I found. Consider a building of height h indicated by PQ in the figure. A person is standing in the window of the building at point O. He wants to observe the image of the building in a mirror. He wanted to place a mirror XY in front of the building. So he has to move a further distance to see the and place at a certain height above the ground, so that because he is standing at point O, which is slightly higher from the ground of the building, foot of the building. So he has to adjust the mirrors at a certain distance from the building and to raise its height so that he can see the full image of the building, that is PQS. So we want to find out at how much height the mirror should be placed in front of the building so that he can see the full view of the building. So for this requirement, the person can see the roof of building P. Standing at O, he wants to see the building top P first. So the light ray starting from P should reach X, that is top of the mirror, top portion of the mirror. From there it reflects back and reaches O. So then only he can see the top of the building. Similarly, he can see the bottom of the building if the ray from Q starts along QY, reaches the bottom of the mirror and reflects back along YO line to the person sitting at home. Unless the light rays coming from top of the building P and bottom of the building Q gets reflected from the mirror from its top portion X and bottom portion Y respectively. Here again, if you remember, the angle of incidence is equal to angle of reflection. So we can calculate the distances. Suppose PQ is capital H, XY is small h, and the person is sitting at O such that the roof of the building is at a height X, so that the the normal drawn from the X point touches the building at R. So that angle of incidence is PXR, angle of reflection is OXR. Because both angles are equal, the PR distance is equal to RO, that is X by 2, X by 2. Similarly, for the light ray coming from the bottom part reflecting back from point O, the angle of incidence and the angle of reflections at the point Y are same, hence OS is equal to OQ. So now if you apply simple geometrical conditions, PR is equal to OR is equal to half X and OS is equal to QS is equal to half of capital H minus X, because OQ is H minus X, OP being X, PQ being H, OQ becomes H minus X. And the length of the mirror XY is equal to OR plus OS, that is equal to half height of the building, half H, half of the building. That is, the minimum length of the mirror to see the full image of the building is, irrespective of the point of observation, X is not coming in the picture, the length of the mirror should be half the height of the building. That is the minimum length required. Then the height at which the mirror should be placed above the ground is, that is given by YZ. That is the height above the ground at which the mirror is placed. This is equal to QS, opposite side equal distance in the building is QS. That QS is equal to PQ minus PS. That is PQ minus RS plus PR. That is equal to H minus half H plus half X. That is equal to half H minus X. So the height at which the mirror should be placed above the ground is half of H minus X. H is the building height, X is the distance from the roof of the building to the observing position. Now, another one. Let three mirrors are fitted in a room. Two of them are fitted on adjacent walls. That means they are 90 degrees. Adjacent means one wall adjacent is second wall at 90 degrees. So two mirrors are placed on adjacent walls and one was placed in the roof. Then how many images are formed in this we want to see. An object is placed inside the room and its images are seen. Then the number of images formed in the two mirrors fitted on adjacent walls, that is angle of inclination is 90 degrees. So n is equal to 360 degrees by 90 degrees minus 1, because 360 degrees by 90 degrees happen to be an even number 4. So 4 minus 1 is 3. So the images seen in the adjacent mirrors is 3. So these three images plus the original image, all the 4 are seen in the roof, in the mirror placed at the roof. Thus the total number of images formed in the three mirrors combination is 4. 3 and 1 original object of 4. So 4 images can be seen in the combination of the three mirrors. Now two mirrors can be arranged in a way such that the incident ray and reflected ray become parallel to each other irrespective of the angle of incidence. So whatever angle it comes, the first incident ray and the last reflected ray from the two mirrors placed at an angle will be parallel. The condition for that we want to see. Let theta be the angle between the two mirrors. I1 and I2 the angle of incidence or reflection at both the mirrors. So the total deviation of the ray in the process is 180 minus 2I1 plus 180 minus 2I2, that is equal to 360 minus 2I1 I2. For the incident beam and the reflected beams to become parallel, this deviation should be 180 degrees. So 2I1 plus I2 becomes 180 degrees, or I1 plus I2 becomes 90 degrees. So from simple geometry, I1 plus I2 is nothing but theta. Thus theta should be 90 degrees. Therefore, two mirrors should be positioned at right angles in order to get the incident and reflected rays to become parallel to each other. Hope this gives you some idea about the phenomena of reflection, properties, and application in some real sense. See you in the next topic of discussion. Till then, bye.